Section: Introduction. In this section, we explore the concept of out-of-distribution OOD generalization, particularly focusing on a type called rule extrapolation. While our model, referred to as LLM, can achieve low training and test losses, a low test loss does not guarantee good performance, especially when the test data is unlikely to appear in the training set. Although modern language models have shown success in OOD scenarios, the theoretical understanding of OOD generalization remains limited. We specifically examine rule extrapolation, which involves analyzing the OOD behavior of language models trained on formal languages defined by a combination of rules. For instance, the language represented by a to the power of n followed by b to the power of n consists of two rules. The number of a's must equal the number of b's, and all a's must come before any b's. A prompt like BBAAB cannot be completed to follow the second rule, but it can still satisfy the first rule by adding an a at the end. When a language model maintains consistency with one rule while another is violated, we consider it to have successfully extrapolated that rule beyond its training data. Previous limited experiments indicated that transformers perform better than chance in rule extrapolation for this formal grammar, even without explicit biases to encourage such behavior. However, it is still uncertain if this behavior is unique to transformers or applicable to other formal languages. Motivated by these findings, we conduct a comprehensive investigation into how different architectures perform in rule extrapolation across various formal languages. We also carry out a small pilot study to see how humans generalize these rules. We chose to focus on rule extrapolation because it seems like a rational behavior, although we lack a clear justification for why it should be considered rational. This leads us to explore how a general rational algorithm for OOD prompt completion could be defined. Instead of merely observing what models do, we ask what they should do based on principles of rational inference. We turn to algorithmic information theory to create a normative model, proposing a non-parametric prior for predicting the next token, inspired by the Solomonoff prior. This prior suggests that a rational model should extrapolate the simplest theories consistent with the training data, even though our rational algorithm, like Solomonoff's induction, is uncomputable. It helps clarify some of our empirical findings regarding rule extrapolation in practical language models. Our contributions include defining scenarios for evaluating sequence models' OOD compositional generalization through formal languages, empirically assessing different models' rule extrapolation capabilities, and proposing a normative theory for OOD prompt completion based on the simplicity of rules. We also visualize the training dynamics of transformers on the a to the power of n followed by b to the power of n language, showing that the model first learns the easier rule before recognizing the language as a subset. In terms of background, formal languages are simplified linguistic constructs that help us study natural languages. They have a clear set of symbols and rules, making them powerful despite not capturing all the complexities of human languages. Formal languages can be categorized into four types based on complexity: regular, context-free, context-sensitive, and recursively enumerable languages. Regular languages can be described using regular expressions, while context-free grammars have rules that are independent of context. We will use simpler examples, such as a to the power of n followed by b to the power of n, and sequences of nested parentheses, to illustrate these concepts. Context-sensitive grammars have rules that depend on the sequence's position, and we will use examples like a to the power of n followed by b to the power of n followed by c to the power of n to demonstrate this. We will not cover recursively enumerable grammars, as they require infinite resources to simulate. Section Summary. In this section, we explore the concept of rule extrapolation as a specific form of out-of-distribution OOD generalization in language models, focusing on their ability to maintain consistency with certain rules even when others are violated. We also investigate the role of different model architectures in this behavior and propose a normative theory based on algorithmic information theory to understand how models should ideally perform in OOD scenarios. Section: OOD generalization. In this section, we explore the concept of good generalization in deep learning. We recognize that the test loss helps us evaluate model performance on unseen data that comes from the same distribution as the training data. When the test loss is close to its lowest value, it indicates that the model can generalize well. Many studies have aimed to establish limits on the generalization gap. Alongside the question of whether the test loss is low enough, we also consider if it has a unique minimum. Identifiability refers to the uniqueness of the model that generates the data we observe. In machine learning, this means that a unique minimum of the test loss corresponds to a specific model, which is beneficial for understanding and interpreting the model's properties. Most theoretical tools focus on scenarios where training and test data are from the same distribution. However, this assumption is often unrealistic, especially in language models that use pre-trained models for various tasks. While some research has begun to address a specific type of good generalization called compositional generalization in vision models, similar studies in natural language are just starting to emerge. Some works have shown that transformers can perform better than expected on certain synthetic grammars, but it remains unclear if this is unique to transformers or the specific languages used. Additionally, there are challenging tasks, like addition and parity, that transformers struggle with without special techniques. Inspired by these findings, we investigate how model architecture influences performance across different formal languages. We introduce the concept of rule extrapolation, a specific type of good generalization. Rule extrapolation involves pre-training a model on formal language data, where the training data includes all language rules. When we present out-of-distribution OOD data that violates some rules, we check if the model can still satisfy the remaining rules. For instance, in the language defined by the rules that the number of A's equals the number of B's and that A's come before B's, a prompt like BBAAB cannot be completed to follow the second rule. However, if we complete it to BBABA, it satisfies the first rule, demonstrating rule extrapolation. We also discuss inductive biases in sequence models like CNNs and GNNs, which are designed to capture specific data structures. The understanding of these biases is still developing. Some studies have shown that language models tend to prefer simpler algorithms. Others have created a formal programming language to analyze how transformers work, proving that they exhibit length generalization, which suggests a bias towards simpler representations. We also note that certain transformer heads focus on specific syntactic relationships, indicating a structural inductive bias. We question whether the good performance of transformers is solely due to their architecture or if simpler models, like linear models or RNNs, can exhibit similar capabilities. Our proposed normative theory reflects on the observed simplicity bias towards low algorithmic complexity, using tools from algorithmic information theory to create an idealized setting for studying OOD prompt completion theoretically. Section Summary. In this section, we explore the concept of rule extrapolation as a form of out-of-distribution OOD generalization in formal languages, where models trained on specific rules are tested on data that violate some of those rules. We also investigate the role of architectural inductive biases in sequence models, questioning whether the observed good performance is unique to transformers or if simpler models can exhibit similar capabilities. Section: Architectures. In this section, we examine when rule extrapolation occurs by comparing 5 different architectures: linear models, LSTMs, transformers, SSMs, with a focus on Mamba, and the new XLSTM. The transformer revolutionized natural language processing by introducing a self-attention mechanism, which allows it to effectively capture global dependencies in both directions, unlike standard LSTMs. SSMs, inspired by dynamical systems, have recently gained traction in language modeling, particularly Mamba, which replaces the attention mechanism with a single SSM block to focus on relevant information. The comparable performance of the transformer and SSM raises the question of whether SSMs can also demonstrate rule extrapolation. We also look at a recent extension of the LSTM that incorporates matrix-valued memory cells, new gating mechanisms, and various computational enhancements. Details about training, dataset sizes, and model parameters can be found in the appendix. Our datasets follow a hierarchical structure. The benefit of classification is that the categories show significant differences. However, this hierarchy is based on computational linguistics concepts, so there may not be a direct link between a language's complexity in the Chomsky hierarchy and what a neural network finds challenging to learn. Each language we analyze follows two rules, where the prompts violate one rule but can still be completed to satisfy the other. Adhering to one rule means the model still follows that rule even when the other is violated, while adhering to the second rule during completion indicates an effort to satisfy it. We define two rules for each language to ensure comparability, although we recognize that these rules can vary in complexity and can be defined in multiple equivalent ways. For regular grammars, we consider two simple datasets. The first language consists of sequences with an even number of A's, and the second language consists of sequences where the number of B's is followed by an even number of A's. The prompts for the first language violate the second rule by starting with an A, but they can still satisfy the first rule. In the second language, the prompts also violate the second rule by starting with an A, followed by B's. For context-free grammars, we implemented two languages. The third language requires matching numbers of A's and B's, while the fourth language involves sequences of nested and paired parentheses and brackets. The prompts for the third language violate the second rule by having B's followed by A's. The fourth language's rules state that brackets and parentheses must be nested and paired, with specific prompt structures that reflect these requirements. Section Summary. In this section, we compare 5 architectures: linear models, LSTMs, transformers, SSMs, specifically Mamba, and XLSTMs, to investigate when rule extrapolation occurs, highlighting the transformer's self-attention mechanism and the SSM's selective focus. We also define 2 rules for each language in our datasets, which include regular and context-free grammars, to assess the model's abilities to adhere to these rules despite certain violations. Section: Context-sensitive grammars. In this section, we discuss context-sensitive grammars. We implemented 2 of them, which we refer to as L5 and L6. L5 consists of sequences where the number of A's, B's, and C's are equal, and it is context-sensitive because the rules depend on multiple tokens. The rules state that the counts of A's, B's, and C's must match, and that A's must come before B's, which must come before C's. We also note that certain prompts can violate the second rule but can still be completed to satisfy the first rule. L6 is a context-sensitive Dyke language, which includes sequences of paired parentheses and brackets, like. The rules for L6 require that both types of brackets are paired. Similar to L4, prompts for L6 start with, and those that violate the second rule start with, followed by matched sequences. For our metrics, we track training and test loss and evaluate the accuracy of the rules separately and together, for both in distribution samples and prompts that violate the rules. We assess the accuracy of the second rule in a lenient manner, either by looking at the completion or, for Dyke languages, the part after the closing parenthesis. For example, for the prompt ab, the completion ab-a is correct for the second rule, while ab-a-b-a-a is not, as it places an a after ab. We limit our evaluation to prompt completions that end with an end-of-sequence token and also monitor the accuracy of predicting the next token using a greedy approach. Our results focus on the minimum test loss to determine if the models are saturated, and we report the highest values for rule accuracies. We also provide a baseline for chance-level accuracy, which reflects the performance of a model that predicts each token with equal probability. We present means and standard deviations across 5 trials and include a non-representative human baseline from a small pilot study, where participants completed prompts after seeing examples. Surprisingly, we found that modern architectures perform poorly on regular languages L1 and L2. Both Mamba and the transformer underperformed compared to the LSTM, with the XLSTM only matching the LSTM's performance on prompts that satisfy the first rule. The transformer's accuracy fell below chance level for in-distribution samples, despite similar test loss to the LSTM and Mamba. The linear model performed well on L2 because it only predicted the end of sequence token on test prompts that already satisfied the second rule. In other categories, the linear model performed at or below chance level. In our pilot study, human performance on L1 was similar to Mamba's. We noted that transformers struggle with tasks like addition or parity calculation, which may explain their low performance on regular languages, as both L1 and L2 require calculating the parity of a tokens. Section Summary. In this section, we implemented two context-sensitive grammars, L_5 and L_6, which require specific token arrangements and pairing rules, and we evaluated their performance against various prompts. Our findings revealed that modern architectures, particularly transformers, performed poorly on regular languages, L_1 and L_2, often falling below chance level, while a simple linear model managed to satisfy certain rules by predicting end-of-sequence tokens. Section: Context-free grammars. In this section, we explore context-free grammars, specifically focusing on languages L3 and L4. For L3, we observe that all four models achieve perfect accuracy on rule R2, both in and out of distribution. However, only the linear model struggles with rule R1 in distribution, while the transformer excels at extrapolating R1, achieving a 66% success rate, followed by the LSTM at 38% and Mamba at 30%. The linear model's seemingly perfect performance is misleading, as it relies on generating an end-of-sequence token. When we look at the Dyke language L4, the transformer again shows the best extrapolation performance, with Mamba outperforming the LSTM. In our small study involving human participants, they performed better on completing R2 than on extrapolating R1, but the transformer outperformed humans in both tasks. Next, we examine context-sensitive grammars, particularly L5, which is similar to L3. Here, the transformer also performs best. The sequences in L5 and L3 are alike, yet L5 is more complex, leading to lower accuracy for R1 in L5 compared to L3. For the context-sensitive Dyke language L6, the transformer and LSTM show similar performance on both out-of-distribution rules R1 and R2. In summary, we conclude that different architectures excel with different grammars. The transformer consistently performs well with context-free and context-sensitive grammars, while LSTM and Mamba are better suited for regular grammars, likely due to the need for parity calculations, which the transformer finds challenging. The XLSTM generally falls between the LSTM and the transformer. The linear model shows limited ability to model formal grammars, failing to minimize test loss. In our pilot study on languages L1 and L3, humans found the tasks challenging, performing better than chance. The LSTM outperformed on L1, while the transformer excelled on L3. We note that our human-machine comparison is more intuitive than a rigorous evaluation, which we leave for future research. We then shift to the normative theory of out-of-distribution prompt completion. We assess how an ideal model should learn and extrapolate rules, proposing a non-parametric prior and prediction scheme for out-of-distribution prompt completion. This can be viewed as a generalization of Solomonoff induction, relevant for language models. Although our algorithm is uncomputable, we believe it provides a rational framework for good extrapolation in autoregressive sequence models. We illustrate our approach with a story. Bob has a language model that generates independent sequences. We define the first M1 elements as in-distribution prompts and the MTH element as its completion. If Charlie, Bob's adversary, generates a sequence that has zero probability under Bob's model, we call this the out-of-distribution prompt. Despite the zero probability, the model can still define the conditional probability of completing this prompt. Charlie then asks Alice to predict how Bob's model will complete the out-of-distribution prompt. We assume that completions are generated independently, using the same model, and we will construct an algorithmic prior based on these assumptions, arguing for its potential in studying out-of-distribution compositional generalization theoretically. Section Summary. In this section, We analyze the performance of various models on context-free and context-sensitive grammars, finding that while the transformer excels in many cases, LSTM and Mamba are preferable for regular grammars due to their ability to handle parity calculations. We also propose a theoretical framework for out-of-distribution prompt completion, inspired by Solomonoff induction, to guide the development of future models capable of effective rule extrapolation. Section: The Solomonoff prior. In this section, we discuss the Solomonoff prior, which assigns a probability to individual data points based on how complex it is to generate them. This concept reflects Occam's razor and Epicure's principle, where simpler data points are more likely. We focus on discrete sample spaces, although similar ideas apply to continuous ones. We will define technical terms for clarity. We start with a universal Turing machine, UTM, and define Solomonoff's universal prior for sequences of any length. We sum over all discrete, lower semi-computable measures that can be implemented on the UTM. We refer to these as mixture components or explanations of the data. The prior on weights is an arbitrary semi-measure, meaning that for all components, the weights are positive and their total does not exceed 1. Often, we choose the weights based on the k-prefix Kolmogorov complexity of each component. Next, we consider the predictive aspect. If the true distribution of our data is known, the Solomonoff prior can make accurate predictions. Our aim is to create a similar prior and predictive method for our task of next token prediction, especially for out-of-distribution prompts, even when our prior might assign 0 probability to those prompts. The Solomonoff prior gives non-zero probability to every possible prompt, meaning it can handle any test distribution as part of its mixture components. However, it can only process one sequence at a time, which limits its ability to separate pre-training from testing. To address this, we propose an adapted version of the Solomonoff prior. We modify it in 2 ways. First, we condition our predictions on a pre-training dataset consisting of multiple independent sequences of the same length. This dataset is sampled from a specific distribution. Instead of treating measures as joint probabilities over sequences, we represent them as lists of conditional probabilities, similar to how certain models handle distributions. This approach allows us to define a mixture over all lists of semi-measures that can be implemented on the UTM. The reason for using lists of conditionals is that there are many ways to factorize joint measures, especially for sequences with 0 probability. If our prompt comes from a different distribution that assigns 0 probability to it, the conditional probability becomes undefined if we only know the joint probability. This issue does not arise in the Solomonoff prior, as it assigns non-zero probabilities to all computable sequences. However, once we introduce conditioning on our pre-training dataset, this consideration becomes essential. Section Summary. In this section, we discuss the Solomonoff prior, which assigns probabilities to data points based on their algorithmic complexity, ensuring that simpler data points are more likely and that all possible explanations are included. We propose an adapted version for next token prediction that separates pre-training and testing processes by conditioning on a pre-training dataset, allowing us to handle out-of-distribution prompts effectively. Section. Starting from a prior weight B group color, Fig blue, $alpha $E group over all possible explanations B group color, Fig blue, $P_I mid, equals P_I, X_K mid X_1 caret K1, underscore K equals 2, caret N $E group. The posterior probability of B group color, Fig blue, $P_I mid, $E group given B group color, Fig blue, $D, $E group is computed. EQ, posterior, right. The B group color, Fig blue, $N, caret TH, $E group step prediction by B group color, Fig blue, $P_I $E group, conditioned on a possibly OOD test prompt, is then weighted by this posterior. It is important that the prediction B group color, Fig blue, $P_I mid, X_N mid X_1 caret N1, $E group is not conditioned on the pre-training data B group color, Fig blue, $D, $E group, and the posterior B group color, fig blue, $alpha, P_I mid D, $E group is not conditioned on the test prompt B group color, fig blue, $X_1 N1, $E group. This, as stated above, separates pre-training from testing, enabling us to define the completion of OOD test prompts. When B group color, fig blue, $D, $E group equals B group color, fig blue, $X_1 N1, $E group, B group color, fig blue, $P_R E group reduces to B group color, fig blue, $P_S E group, and thus the posterior prediction converges according to EQ. Predictive_convergence of Solomonoff_prior. In this section, we interpret the process of calculating the posterior probability of various explanations based on prior weights. We start with the prior weight over all possible explanations and compute the posterior probability given our data. The prediction at the nth step, based on a potentially out-of-distribution test prompt, is then adjusted using this posterior. It is crucial that this prediction does not rely on the pre-training data, and the posterior is not influenced by the test prompt. This separation allows us to effectively handle out-of-distribution test prompts. When our data matches the previous inputs, the prediction simplifies, leading to convergence as described in our earlier work. For out-of-distribution test prompts, multiple explanations can align with our data. Thus, the behavior of our predictions, even as the amount of data increases, is influenced by the prior weight we choose. This is different from the Solomonoff prior, which consistently converges to the true posterior regardless of the weights. Therefore, we select a prior that favors simpler explanations consistent with the data, using a method that penalizes longer programs that can approximate our predictions. This approach incorporates Occam's razor into our prior and aligns with the optimal weights of the Solomonoff prior. We have defined and tested rule extrapolation in simple formal languages, where our analysis is manageable and shows that models can extend beyond their training data. However, we recognize that our datasets do not fully represent natural language, where demonstrating rule extrapolation may be more challenging. Studying formal languages remains relevant, particularly for programming languages or formal mathematics. Although we explored various hyperparameter settings, we did not conduct exhaustive tests or analyses of different model architectures, which could influence our results. Rule extrapolation represents a specific case of compositional generalization in language models. While other types of out-of-distribution generalization have been studied, our work is the first to focus on rule extrapolation. This new concept could significantly influence research in large language models, both theoretically and practically. General compositional generalization looks at whether a model can understand the combination of learned concepts, while rule extrapolation examines if the model can separate these concepts from their combinations. This reverse approach is less straightforward but allows for a clearer study of compositional generalization across various datasets, making rule extrapolation a potential benchmark for evaluating current and future language model architectures. We would like to express our gratitude to George Flamich for insightful discussions on Solomonoff induction, Bence Naiki for practical insights into natural language processing, and Gail Weiss for her contributions regarding probabilistic context-free grammars. Our work received support from a Turing AI World Leading Researcher Fellowship and various institutions, including the German Federal Ministry of Education and Research. Patrick Reisinger acknowledges his involvement in the Ellis PhD program and appreciates the support from the IMPRSs. Additionally, we recognize the financial backing provided to Wieland Brendel through various grants and institutions, as well as the computational resources utilized from the Tübingen Machine Learning Cloud.